In this video, we'll talk about quadratic functions. So we've already talked about polynomial functions of various degrees, and we'll motivate our discussion about quadratic functions by starting there. But quadratic functions are very useful to model real-world phenomena. So we'll start talking about polynomial functions of degree n. We'll go into minimizing that to degree 2. And then we'll talk about standard form, and we'll find the maximum or minimum value of a quadratic function. So we know polynomial functions of degree n look in general like this. We start with some constant and some variable to the nth power, and then another constant with a variable to the n minus 1th power, etc. and so forth. We've talked about polynomial functions, quote, quote, of degree 0 and 1, like we know what p of x equals a looks like. We know that that's just, that's just a line. Specifically, that's a horizontal line. And we know what a graph that looks like p of x equals ax plus a1x plus a0. We know what that looks like. That's a line with some slope a1. So now we're going to extend our discussion to polynomials that look like this: ax squared plus bx plus c. Of course, if a equals 0, then we don't have a polynomial of degree 2, so we specify that a will not equal 0. So the standard form of a quadratic function. Quadratic function f of x equals ax squared plus bx plus c can be expressed in standard form f of x equals a quantity x minus h squared plus k by completing the square. The graph of f is a parabola with vertex hk. The parabola opens upward if a is greater than 0, or downward if a is less than 0. And this we just know from our discussion on shifts and transformations of various functions. We know that if we have a negative in front of the function, in this case the x squared, then it flips over the x-axis. By the same line of reasoning, we know that negative h implies we're shifting to the right. If we had a positive h, we would be shifting to the left, and a positive k up, negative k down. So that can help frame the shifts and translations of a parabola, thinking about where its vertex lands and which direction the parabola opens. So thinking about this standard form of the quadratic function, if we have f of x equals a x minus h quantity squared plus k, if we want to graph this and gather some information from the standard form of the function, all we have to do is take a look at a, h, and k. So a, we already said, if a is greater than 0, opens upwards, and if a is less than 0, the parabola opens down. Then we can find a minimum or maximum for the parabola based on the vertex. So we know that if we plug in f of h, that'll give us a times h minus h squared plus k. So that'll leave us with f of h equals k, which that's just our vertex hk. However, this information in combination with this information can tell us whether the vertex is a minimum or maximum value of a quadratic function. And this is really useful for when we're modeling real-world scenarios. If we want to find out where, the maximum production rate is for some factory, or the minimum cost for producing something, this is a really useful technique to algebraically find if a relation has a minimum or maximum in the parabola. So the maximum or minimum value of a quadratic: if f is a quadratic with standard form f of x equals a times the quantity x minus h squared plus k, the maximum or minimum value occurs at x equals h. If a is greater than 0, then the minimum value of f is f of h equals k, and if a is less than 0, then the maximum value of f is f of h equals k. I've got two figures here just to kind of help frame. So on the left we have f of x equals a x minus h squared plus k for a greater than 0. So we open upwards and we've got a minimum at the vertex. And on the right, we have f of x equals a x minus h squared plus k for a less than 0, which would imply that our vertex is a maximum. But suppose we're not already in standard form. We should be able to take another approach. If we don't want to complete the square for some quadratic that we're given, there's another technique that we can use. So let's say we have f of x equals ax squared plus bx plus c. Let's kind of complete the square with this. So first let's factor out an a from the first two terms. So we have a x squared plus b over a x plus c. Next, let's complete the square inside the parentheses. So let's add b over a over 2 quantities squared. So that'll be a x squared plus b over a x plus b over 2a squared. And then, of course, outside of the parentheses, we must subtract that same number. So we have to subtract b over 2a squared. Lastly, we factor what's inside the parentheses, so we end up with an a x plus b over 2a quantities squared plus c minus b squared over 4a squared. So this is the equation of a quadratic function in standard form, but now we have h equal to negative b over 2a. And in this case, k equals c minus b squared over 4a squared. So we can kind of recognize the same structure of the standard form, that is f of x equals a times x minus h quantities squared plus k. So with this information, we can equivalently phrase the maximum and minimum value of a quadratic function as the maximum or minimum value of a quadratic function f of x equals ax squared plus bx plus c occurs at x equals negative b over 2a. If a is greater than 0, then the minimum value of f is f of negative b over 2a, and if a is less than 0, then the maximum value of f is f of negative b over 2a.